Okay, in this video we're going to talk about how we determine the present value of a continuously varying payment stream when the force of interest could also be varying. So take a second here to pause the video, write down the notes, and then we'll go through things. All right, so I want to remind you a little bit about what happened back in Chapter 4. Chapter 4, you talked about constant force of interest and a certain amount of money at a particular given point of time, and you can figure out the present value by looking at that accumulated value at time t, and then bringing it back using our normal exponential formula for the force of interest. Chapter 5, you changed things up a little bit. You varied the force of interest with a delta t formula. So in that case, you took your chunk of money there at the end of the time, the t, and you had to bring it backward using that integral formula back to time 0. The only reason we have ds here rather than dt is because I used t for time, and then I didn't want the variable of the integration being the same as what was up in the limit of integration. In Chapter 7, you learned about continuously paying annuities with a constant payment stream. You also talked a little bit about increasing annuities at that point with continuously paying. But again, for each time period, the chunk of money that you were getting was constant over that time period. So we're actually going to do another form of increasing continuously paying annuities where the money changes all of the time, continuously, not just chunk of money, chunk of money, chunk of money for each time period. All right, before we get to there, though, let's just talk about this in general. So we're going to have the payment rate at a given time, per unit time at a given time t. We're going to denote that with this x sub t part here, and we're going to do the force of interest with a delta t part here. So again, when we're going to do this, the things are happening continuously. We're going to have to get a handle on it in a non-continuous fashion first, and then do what we would do in calculus by taking a limit, and then the limit will change things into integrals. So just to show some things here with a time value diagram, let's say we split up each of our time intervals from 1 to n up into m subintervals. So notice here we chopped up that 0 to 1 part into 1 over m chunks. So I've got a 1 over m, 2 over m. I've got this arbitrary k part somewhere in the middle, and then all the way up to n. I've also labeled the payment numbers here at the bottom that we have, because I'm going to refer to those back here on the right side of the screen here in a minute. But again, what we're going to do, just like we do in a calculus fashion, we're going to use a constant approximation for a small subinterval, and then let the subintervals get smaller and smaller to get to the formula that we actually want. So these x sub 1 over m's, we're going to use that, say, the right-hand endpoint like you do in Calc 1, the right-hand endpoint to evaluate the constant, approximate the payment stream for the 1 over m time period. Remember that x sub t is representing a payment per unit time. We're only going to use that for 1 over m length time, all the way through. All right, so if we want present value of this stream, we need to be able to bring it back using our force of interest ideas. This is just using a Chapter 4 idea, like we said before. So the first payment, I just need to step it back 1 time interval. Again, we're going to have to approximate the force of interest on that time interval. So that's what these delta sub t's are doing here. They're going to approximate the force of interest. So for each t, we will use delta sub t to approximate the force of interest. So at the first payment, we've only got to step it back 1 time interval. For the second payment, I've got to step it back 2 time intervals. I've got to get it from 2 over m to 1 over m, and then 1 over m to 0. So that's why I've got both of these exponentials. I've got an e to the negative delta sub 2 over m and an e to the negative delta 1 over m. Notice here, when I combine these, I would add the exponents. So you can go through, if you want, and look at the k times m payment, or what's happening here at time k. Well, we've made km payments, so we're going to have km of these step backs to get back to time 0. Each time, the delta is going to change that we're using for our approximation. We've only got the 1 payment we've got to step back, but we've got to step it back all of those time periods. So that's why we've got this weird-looking summation formula up here in the exponent. But again, that's just because we're multiplying by an e to the negative delta factor each time, and then stepping it back that many time periods. So to get the present value of the stream, I need to add all of these things up. So that's all I've done here is write that as a summation notation. And I moved that 1 over m piece in the payment out in the back. So if you remember again from calculus, we recognize this 1 over m as a delta x kind of factor, or a delta t in this case since we're talking about time, factor. So when we take our limit as n goes to infinity, making these subintervals get smaller and smaller, both of those summations are going to turn into integrals. So we've got the integral from 0 to n. That's the length of time that our payment stream is coming in. X sub t is the amount of payment, that's the payment rate per unit time. And we've got e to the negative 0 to t of our force of interest up here, again, just using an s rather than a t because we don't want to mix our variables with our variable of the time with the limit of integration, and then dt. This is the important formula that you'll need to know, and we'll see in the next video that a lot of these problems are formulated so that you can do these integrals quite easily.